And we're back. Welcome back and happy Thursday. Today we'll switch gears and look at an alternative treatment or analysis of learning complexity, namely bias variance. But before we begin, some administrative bits. The sections in the book related to growth functions, VC dimension, and lastly, bias variance. So where we last left off, we talked about the VC inequality, namely the VC bound, and we took that bound on the probability that E in diverges from E out, that is hopefully small, and we rearranged it and solved for epsilon, our error tolerance. So then we looked at the relationship between E out and E in and looked at the complement of this event for bad things happening and developed the expression E out minus E in is at most this complexity term omega that is indexed by the data set size, the hypothesis set, and our delta, this bound. We took that expression and it gave us a relationship between E in and E out modulated by this complexity measure. And so you can use your complexity as defined by that interaction between the probability of bad things happening, the hypothesis set, and the data set size to ensure that E in is closer to E out. And you can try to impact how you approximate E out by controlling the complexity of our models. And there's a technique called regularization, which does exactly that. So let's look into our alternate treatment, bias variance. And so in learning, there's a trade-off. You want a very small E out, and you want to have a good approximation in your unknown target function F. You want your final best hypothesis to be a good approximation. And you want this approximation of target function to perform well on new data, to perform well out of sample. And so you want E in to be a good approximation or express a good approximation of your target function. You control in-sample error, but you have no control out of sample error. And so with a very sophisticated hypothesis set, something you can control, you could make it so big that you have a really good chance of approximating F. But the problem is that the information that you have about this unknown target function is given only through the samples. And so the problem becomes one, then, of identifying a good hypothesis from among the working hypotheses drawn from your hypothesis set. And so you have to navigate through your hypothesis set, enterprising, to find a good working hypothesis such that when your learning algorithm halts, it will result in a good G, your final best hypothesis. And so how you do this navigation is using your data set. You actually can't see the target function. Maybe it's even inside that large hypothesis set. You can't see it. And therefore, you're unable to select it, even if it is inside of a very large hypothesis set. And so having a less complex, a notionally smaller or less complex hypothesis set means you have a better chance of performing well out of sample or generalizing. And we see that with the degree of the polynomial for the VC bound when we replace this growth function with a sample size of 2n. We said if it's polynomial, the complexity, then it will be subsumed by this decaying exponential in the VC bound. And so what's the best hypothesis you can get? Well, the smallest one will only have a single hypothesis, this hypothesis set, and the best one would be a singleton hypothesis set that contains a single function that's exactly the unknown target function. And so, but that's not how things really work in practice. And so the VC dimension handled that trade-off in using a probabilistic bound on the difference between your hypothesis, your final best hypothesis, and your target function, we developed the VC bound. And as VC bound said, if the conditions are right, you make the right trade-offs, that it's very rare that in-sample performance and out-of-sample performance of this final best hypothesis will diverge from one another. And the VC analysis, moreover, said that by striking this balance, choosing the right complexity, omega, that E in and E out will be very close to one another, even if you don't know what E out is. And so the bias variance is a competing analysis, and it decomposes your out-of-sample error into two things: an expression of how well the hypothesis set is able to approximate your unknown target function, and how well you can approach it or identify, search for a good working hypothesis drawn from your hypothesis set. And so we're going to use an example where we apply this to real value targets using squared error, just to make things a little bit simple, but the concepts are still the same. And so in this example, we're going to examine E out. This is our out-of-sample error. And this out-of-sample error, we're going to have relative to our final best hypothesis, G. Now, this final best hypothesis is dependent on the finite data set that you have. And so we're going to index in this notation our final best hypothesis, G, with the superscript, script D. And that's going to represent a unique or particular final best hypothesis that you arrive upon when you're given a data set. Because if you choose a data set and you run your learning, you get a certain final best hypothesis G. If you choose a different data set, finite data set, you're going to get a different final best hypothesis G, even if the data set is the same size. And so here we index our final best hypothesis G by the data set, and we say our out-of-sample error is the expectation with respect to that probability over our vector instantiations of the square of the difference, so it's a squared error loss, between our final best hypothesis on each of those inputs in the data set and the unknown target function. And so this is a variance in the traditional sense. And so the E out is with respect to the final best hypothesis, and we're going to index this by a data set. And this is computed as an expectation over all instances in an arbitrary data set, and you can make the assumption that all the data sets are the same size. So if these data sets, or if this final best hypothesis depends on the data set, we would then also compute our expectation of this E out with respect to all possible instantiations of data sets. And so we're going to take the expectation with respect to the possible data sets, and since this expectation, when we do that, we have our original expression for E out. So here's our E out, and then we're going to take that expectation of that E out with respect to the data set. Now, in expectation, because it depends on an integral for real valued quantities, which these data sets are, we can swap these expectations. So we can put the expectation with respect to the data set inside and bring out the expectation with respect to the instantiations of the data points. And so when we do this swap, we're going to now focus our attention on this inner expectation with respect to the data sets, E script D of our final best hypothesis indexed by a data set on X, that difference, squared error difference between our final best hypothesis and our unknown target function. All right, so let's take that inner expression, and before this, we're going to take a look at this notion of what it means to take the expectation with respect to different instantiations of data sets on our final best hypothesis for a given X. And so we're going to call this G bar. And this G bar is the average hypothesis. It's the average value given by our hypothesis for an input instantiated over all possible data sets. And so if you have some finite number of data sets, D1, D2, D3, up to and including DK, you're just going to take as your G bar the average of the output of the final best hypothesis for each of those data sets with respect to that input X that you give it. And so this average G bar, is going to be our average hypothesis. And thinking about it, it's the best hypothesis that we can have in general. It's the average among all the possible data sets that the final best hypothesis will output, given some input X. So let's take this expression, and we're going to expand this and come up with an expression that will characterize the performance trade-off of the complexity of our hypothesis relative to E out. All right. So we start out with our expectation, and it's trivial to take this G script D of X and add 0 and then subtract our F of X quantity squared. And so if we add a 0, one way to add that 0 is to subtract G bar of X and add G bar of X. It doesn't change the expression mathematically at all. And so we have now our expression, our expectation. The new version of our expression is the expectation with respect to the data sets of quantity squared. We have the G indexed by the data set of X minus G bar of X plus G bar of X minus our unknown target function F of X quantity squared. And so now what we're going to do is we're going to group together these first two terms, the G script D X minus G bar, and we're going to group together by associative rule this G bar of X minus F of X. And so if we do that, we get G script D of X minus G bar of X plus G bar of X minus F of X. And we're going to do the square of this entire thing. So we have two parenthesized expressions. Here's my first term. Here's my second term. And I have these two terms added, and I'm going to square the whole thing. So I'm just going to apply the FOIL rule. So it's the first term squared plus the second term squared plus 2 times the cross term, which is the first term times the second term. So here's my first term squared. So that's G script D of X minus G bar of X quantity squared. That's the first term squared. Here's my second term squared. It's G bar of X minus F of X quantity squared. Okay. So now here's my cross term. 2 times the first term, that's the G script D of X minus G bar of X times G bar of X minus F of X. That's my cross term. So that's 2 times the first term times the second term. Okay. So now that I have this expression, I know that if I have the expectation of the sum of a number of terms, that's the same as the sum of the expectation of the individual terms. So if I focus first on this cross term here, I take the expectation of 2 times G script D of X minus G bar of X times G bar of X minus F of X. And so if I have this expectation, well, in computing this expectation, I observe first this second term in this product. I have a 2, which is a constant. I can bring that out because the expectation of a constant is this constant times expectation. And we note that this second term here does not involve this data set, this script D, and it is a constant underneath this expectation. I could also bring this out that looks like a constant. So that's going to give me 2 times G bar of X minus F of X times the expectation of G script D of X minus G bar of X. Okay. So now, again, I have the expectation of the sum, and subtraction is just the sum adding the negative, is the sum of the expectations. So if I do the expectation of this first term, well, that's just the expectation of g script d of x, and it's the expectation with respect to the data set. And what is that? Well, we have from the previous slide, that's nothing more than just g bar of x. Okay, so if we compute this expectation, this term becomes g bar of x, and this first term in our cross term goes to 0, because g bar of x minus g bar of x is just 0. And so this entire term is going to drop out, because we're going to have 2 expectation 2 times this g bar of x minus f of x times 0, which is just 0. So this leaves us with this second portion, and that second portion here is just the expectation, e script d, of our first term, g script d, the data set of x, minus g bar of x, quantity squared. And the expectation of the second term, well, this does not involve script d, so that's just a constant. So we're going to get plus g bar of x minus f of x, quantity squared. So this is exactly what we get. Now, if we look at these terms, this first term on the left-hand side of equality talks about how far you are from the target function on average across all data set instantiations. And this right-hand side of equality consists of two terms. The first one is how far your hypothesis is from a particular data set, for a particular data set, how far your final best hypothesis is from the best that you can do across all data sets. And so this g bar of x represents all data sets, and this g script d talks about final best hypothesis for a given data set. You take the expectation to say across all the data sets on average, how far is your best hypothesis from the best you can do, this g bar across all data sets. The second term is the distance between the best hypothesis you can have, the average hypothesis, and the unknown target function. And so this first term is called the variance, and this variance represents the way you search for the best hypothesis. How you search is dependent upon your data set, and you can arrive upon a different final best hypothesis based on your data set. The bias represents the limitation of your hypothesis set, how descriptive it is, namely how far off the best you can do will be from this unknown ground truth target function, and that's your bias. And so we didn't forget about this outer expectation. We started out, when we got this bias and this variance treatment, we swapped the expectation with respect to data sets with the expectation with respect to instantiations of the x data points. And so if we take our expression and we put back in this outer expectation with respect to x, we get the expectation with respect to x of the bias associated with x and the variance associated with x. And this is just the bias plus the variance. And so this decomposition, the so-called bias variance decomposition, talks about your out-of-sample performance consisting of two components, namely the bias, how far off your best average hypothesis is from the target function, and the variance, the way you search for it, the average difference between a particular hypothesis and the best you can do. So let's visualize this graphically. Now, on the left-hand side, we list the bias. And this bias is the distance between your average best hypothesis, G bar, and your final your unknown target function, F. And so if your hypothesis set is very small, well, what happens? If it's small, the bias is going to go up. It's less expressive, but the variance, the differences that this G can have, is going to go down. If we direct your attention to this graph or this figure on the right, here our hypothesis set is really big. And let's say it's so big that our ground truth target function is inside of this hypothesis set. And what we see then, we have many different choices for selecting our final best hypothesis. If you select a final best hypothesis G for one instantiation, maybe it's over here. Maybe it's over here. Maybe it's over here. You get a lot of differences. And so the variance then is this red region. It's the set of differences or different final best hypotheses you can get as you have different data sets that you draw. Now, even though your unknown target function is inside your hypothesis set, you have to find it. And so finding it means you have a sample, and then you train, you learn, you search, and depending on that data set, you're going to get a lot of different versions of your final best hypothesis G. So there's variability in all those versions. And so if your hypothesis set is really big, we see your bias goes down because the best you can do, which would be right in the middle of this cloud of variability, is very, very close to your unknown target function. But the variance, the set of alternatives, is going to get much, much larger. So a big hypothesis set means that your bias will go down because it's more descriptive, but the variance is going to go up. And so you need to strike that balance between the bias and the variance. The sum of the two needs to be small in order to generalize well out of sample. And so let's take a complete example. And in this example, we have a sinusoid, sine pi x, as our ground truth target function. And I'm going to show you this sinusoid. And the data set is going to be fixed to be a data set of size 2. So n is equal to 2. And so what this sinusoid is going to do, it's going to take a value between minus and plus 1, and it's going to output a real number. And so we're going to have two different hypothesis sets for learning. We're going to have a constant line, and then we're going to have a line on the plane. So the constant is h of x is just b. It's going to be a line just going straight across. And then h1, our second hypothesis, that's more complex. It's going to be a line. So it's going to have mx plus b, or ax plus b. And so the question then that we ask is, given this data set of size 2, that's all you have is 2 data points, which is the best model that you can use to fit or approximate this unknown target function? And I'm just showing it to you. And so let's start with just approximating the target function. We take the target function as a known thing, and then we ask the question, what is the best hypothesis from H0 and H1 that comes the closest to mimicking this unknown target function? And then we compute out of sample error as just the mean squared error for this approximating fit, this best fit. Now, of course, you can't do this in practice because you don't have access to the unknown target function, but this will just give us a baseline to show you that this G bar really does give you something very, very close to the best you could ever do. So here we take our H0 and we do the fit. It's the constant 0, and it goes across and it's exactly 0. If we take the mean squared error, well, out of sample error is all of the yellow region. We take the mean squared error between our best fit H0, which is just straight across the 0 constant line, and and we compute mean squared error, we get out of sample error is equal to 0.5. And this is the best approximation of the sinusoid that we can make with a constant function as measured by mean squared error for our approximation error, or out of sample error. If we do the same thing with the line, the linear function, now this linear function, we do similarly. We make the best fit, and we get the following line best approximates this sinusoid. Again, we take the mean squared error, it's this yellow region, and we get this mean squared error out of sample is 0.2. So one observation to make is that the hypothesis set H0 is a smaller hypothesis set than H1. We see that the bias for E out, or E out for the constant function, is bigger because it's a smaller hypothesis set. The bias E out for the H1, the line, which is a bigger hypothesis set, is smaller. So that's an important observation. We make the hypothesis bigger, and this approximation error goes down, and that's just like our bias. But it's not bias in the sense of learning. This is approximation error, ground truth, what E out is respective to the best final hypothesis, the best we can do for the constant function, and the best we can do for the line. So let's look at what happens in learning. Now again, we said that we have two data points. So we're going to bring back the target function, and we're going to measure out of sample error, but that's based on the best fit for the in-sample data. And so here we draw two examples from the sinusoid, randomly sampling, and we then take those two data points and we ask the question, what is the best line or hypothesis drawn from H0 for those 2 points and H1 for those 2 points? And so here we're learning using a constant function from a sample of two examples. It's going to be right in the middle of the y component of these two samples, so this green line for those 2 points. And then for the line, we're going to have the best fit line going through those 2 points that we sampled from the sinusoid. And so in this case, the error is going to be dependent on the data set. If we have a different set of 2 points, we're going to have different errors. And so we're going to bring back our target function, and we're going to measure out of sample error. But this time, we're going to do it based on our data points, and this is more like what happens in learning. And so let's take a look at our bias and variance. So we're going to, in a series of rounds, we're going to pick different data sets. We're going to pick 2 points, find the best hypothesis, pick 2 points, find the best hypothesis, pick 2 points, find the best hypothesis, and keep doing that for the H0, the constant function, as well as the line, which is H1. So let's look at H0. Now, for each 2 points picked from this, sampled from this function, we're going to find the best fit line, and we do it again and again and again. And you can see it's dependent on the data set, our final best hypothesis. And so then, for all of the different final best hypothesis G that we get for each sampling of 2 points, we're going to compute the average. And lo and behold, this average is right here, this constant function going across. It looks a lot like that best fit approximation when we knew what the target function was. And then if we look at the variance, we're going to depict that as one standard deviation in the value of G across all of our data sets. And that's this gray region. So as you can see, for H0, well, the variance is relatively small, this gray region. But we saw from before the bias is very large. If we look at the mean squared error between G bar and this line, it's going to be quite large. If we look at hypothesis set H1, we again sample 2 points, fit the line to those points, find the best line, sample 2 points, find the best line. Keep doing that some large number of rounds. compute our G bar, the average line across all of those rounds of sampling 2 lines and picking the final best hypothesis G from H1. This is our G bar. And it looks a lot like that approximation, that best approximation from H1 when we knew the target function. And if you look at the variance here, the gray region, you notice that variance is much larger, this gray region. But the bias, the difference between this G bar and this target function, if we were to take the mean squared error, it would be smaller. A bigger hypothesis set, H1, has a smaller bias. The difference between G bar and our target function, a smaller bias, but a larger variance, a larger gray region. So let's now calculate this. And so if we measure the bias across all the data sets, we look at the G bar and its difference with our target function, well, we get a bias of 0.5, and lo and behold, that's exactly equal to the approximation error by mean squared when we knew what the target function was. When we measure the variance, the gray region, that's 0.25, okay? Let's direct our attention to H1. When we measure the bias, the difference between this G bar and the target function, well, that's 0.21. That's very close to the approximation error, mean squared error, when we knew what the target function was. That was 0.20. So it's very, very close. But when we look at the variance, that's where things go horribly wrong. The variance is absolutely huge, catastrophic almost. And so now the learning problem then is, given that you have a data set of size 2, and you know that it's from some unknown probability, and you have an unknown target function, which is better, H0 or H1? And so we see here, if we add the bias and the variance together, for H0, bias plus variance is going to be 0.75. And if we add bias and variance for H1, that's much, much larger. It's 0.697989, 0.19, which is much, much larger. And so that means that H0 is a better choice of hypothesis set for this learning problem. And so the lessons from this is that when you're matching your model complexity or trying to find the right model complexity for your hypothesis set component of your model, you want to match your model complexity to the data resources, not to what you believe the target function complexity is. What you learn depends directly on the data that you're given, the data that you have. And so the question you should ask yourself is not, is the target function there? Rather, do you have the resources to find it? So you are to pick a hypothesis set that you can afford to navigate given the data resources that are available to you. And you have no control over those data resources. They're just given to you. All right. So with that, we'll end there. And as usual, please stay healthy, stay safe, and I will see you all on Tuesday.